Again, good morning to all. So this morning we'll be tackling bipolar junction transistors or BJTs. So the BJT is another major electronic device that you should learn. You should understand how it works, and you should also know what is its functions and applications. So the BJT. BJT is just only one of the two major flavors or categories of transistors. The other one is the field effect transistor or FET. Ito siguro mga topic mga few weeks from now also. So the BJT, siguro ito first i-compare ang BJT sa atong previous na electronic device, which is the diode. Okay. So unlike the diode, which I'll review here, unlike the diode, which has two terminals, the anode and the cathode, positive terminal and the negative terminal. Our BJT has three terminals. BJT. So yung schematic symbol is this one. Although there are two types of BJTs, atong ma-introduce later on sila. The more common one is this one, akong i-draw. So our BJT has three terminals. Okay. Ang atong diode has only one current passing through it and one voltage across it. The voltage across it is this one, VD. And the current passing through is this one, ID. So unlike our diode, the BJT has three pairs of currents and diodes. So, or actually, three currents and three diodes, three voltages, I mean, sorry. Three currents and three voltages. So, asa yung mga current dire? One is this one. Another is this one. And another is this one. So, later at naman label lang sila mga names. The voltage drops across the diode are these. Na voltage drop between this terminal and that terminal. Ako voltage drop between conventionally negative ata nila. No. So napoy voltage drop between this terminal and that terminal. And napoy voltage drop between this terminal and that terminal. So we have three currents and three voltages. So far, compared to the diode, to the diode's electrical parameters, these are the electrical parameters that we'll be measuring or calculating sa BJT. So what is a BJT then? So a BJT or bipolar junction transistor, in terms of its structure, has three regions called the emitter, the base, and the collector. So katong tulo ganina na terminals, those correspond to three regions. Supposedly these three regions are where those terminals are connected. So ang mga terminal na to is most definitely metallic contacts man. So those metallic contacts are then connected to a semiconductor material. So a BJT is a three-layered electronic device. It either could be an NPN BJT or a PNP BJT, depending on the semiconductor material that it's made of. So for the NPN, of course, it is made of two N layers sandwiching AP layer. Okay. So, in the same manner, ang PNP, i-sandwich ang N layer with 2 P layers. Okay. So, these illustrations are actually not done to scale because ang actual ani, dili gyud ingani ka baga ang P junction. Actually, nipis na siya. Hundreds times thinner compared to the N regions. Dako na kaayo ni siya. Dako na kayo na siya nga size or dimension. Pero just for visualization sake, we could think of the BJT as a sandwiched electronic or sandwiched semiconductor material. So the two layers, siguro major layers na ginasandwich ang mas smaller na layer, we designate them as either the collector or the emitter. So muna yung mga pangalan sa mga terminals nila. Very important try to familiarize them as early as now. So we have the collector and the emitter. So if NPN, kung NPN, both the collector and emitter are N-type materials. If PNP, just like the image on the right, if PNP, both P's are the collector and the emitter, respectively. So ang sandwiched material, the material on the middle, is the base, or will always be the base. Base. So ang nasa ito nga ang base, same sa PNP. Sa PNP, ang base is N-type material. Sa NPN, ang base is P-type material. Okay. So I'll draw again the schematic symbol for BJTs. Again, it either could be an NPN or PNP. First, dota og horizontal aron ng vertical line, kung naka-manner ang atong BJT. Then, connect atong terminal. Dota og diagonal na slant lines. Then, i-connect nato na og terminal. Okay. So, basically, this is the schematic symbol for our BJT. Now, how will we differentiate? Sa IP, na doing circle, pwede na po wala. How will we differentiate if it is an NPN or PNP? Ano itong arrow? So, isa ani nila, either convention niya ang nasa bottom na portion, ano itong arrow? If the arrow is pointing downward, okay, that is an NPN na BJT. Similarly, the arrow is pointing inside, that is a PNP na transistor. So, yung mga terminals, kung asa nakakonect ang horizontal line or vertical line, siya ang base, or nasa tunga. Kung asa ang may arrow na symbol, siyang emitter. And lastly, ang nasa taas, conventionally mo na siya ang collector. May times nga ang collector sa silong, or pwede ka din ang pag-draw sa BJT is ana, so base gihapon emitter gihapon na siya, collector na siya. May times nga bali, ang arrow is na-adere. Okay. So, huwag gihapon ng emitter, collector, then base. Again, kung asang arrow, itong emitter, kung asang line, whether horizontal or vertical mo itong base. And nabili ng isang collector. So the base is a thin, actually thin gid dapat kaayo. Lightly doped region compared to the heavily doped emitter. So mas heavily doped ang emitter compared to collector, which is moderately doped. You know, previously that doping is the process of adding impurity atoms, not to silicon. So what are examples of impurity atoms? We have boron and antimony. No? So kung punta na to boron or antimony ang silicon, amount of impurities determine kung sa siya ka heavily or lightly doped. So that's dope. BJT operation. In normal operation, the base emitter is forward bias and the base collector is reverse bias. So we have these terms again, biasing. Unlike before, sa transistor, sa diode, either naka-forward bias or reverse bias ang atong diode, right? For the BJT, because we have three regions, because of the three terminals, katong silang tulo ka regions will either be reverse bias or forward bias. So dili lang kay isa ka region ang atong timanan, but this time tulo, no? So tungod kay tulo, technically we have six, maybe six possible outcomes for the biasing of the regions of the BJT. So I think only two are useful to us. Actually, only three day. Not all of them. So in normal operation, nato na i-quantify ng word na normal. Hindi na technically normal in essence nga other biasing compared aning what's stated here is not normal. Let's quantify this word normal. In maybe Bjts Amplifier, operation, not only we should not use the word normal lang when referring to the BJTs amplifier, kay pwede mo gamitin ng BJTs switch, and it's still normal. It's still normal to use the BJTs switch. Siguro sa'yo pang slide. So when using the BJTs amplifier, the base emitter is forward bias and the base collector is reverse bias. So asa nato na siya ma-observe sa atong BJT. Again, let's draw the schematic symbols for our BJT. This time I'll use NPN. Most of our discussions will be using or utilizing the NPN unless i-state na ko otherwise. Anyway, bala na to if NPN or PNP. Depende sa arrow. So, this is a symbol for NPN transistor. Emitter, base, collector. So later lang ang current. Ito sa voltages. So we have three voltages when referring to the BJT. Mentioned earlier, diba? Sa kanina slide. So we have three voltages. This one, that one, and this one. So ito lang ibang label. We have voltage. voltages. First, VCE. Voltage across the collector and the emitter. So VCE. We also have VBE. The voltage across the base and the emitter regions or terminals. And last, we have voltage VCB. Voltage across here. So if not a voltmeter, that sa terminal is is dito. So natin ma-measure nga voltage drop. Okay. But the same with other voltages or transistor voltages. Okay. So for amplifier operation, the base emitter daw is forward biased. So the base emitter is forward biased. So if we use our transistor as an amplifier, gamit ito siya sa amplifier na circuit, ang base emitter, this one should be forward biased. So meaning dapat positive ni and kani negative. Okay. So BJT is amplifier. And the base collector is reverse biased. Base collector is reverse bias. So if reverse bias ni, I think yung polarity, plus minus. How about the collector emitter? In effect, ma-forward bias na siya giyaha. So importante lang is the base emitter and base collector. For the NPN type shown, the collector is more positive than the base. Tabunan siguro ang NPN nga visual. For the PNP type, the voltage are reversed to maintain forward bias. Reverse bias niya siya because of the source. No? Pero if atong source kay plus minus, yes, I think sakto man ni, no? The negative positive dapat kaya po na siya. Sige lang, no? Doesn't matter. Patalan ng ma-expound later. Okay. So BJT as amplifier. We have learned from the previous video kanina that there are two main applications of transistors. Whether BJT or FET, mga gid ni siya ang main application for transistors. And we already mentioned these two. One is that the BJT could be used as an amplifier. When we say amplifier, ang very basic lang yung definition. No? So we have a signal and this device is able to increase its magnitude. No? So yan na lang. Maybe lahi ang nasa tong mind when we hear of the word amplifier. No? Wasig amplifier system na ito masabot. Katabi na nasa balay, no? Amplifier system na ang amplifier device mismo and naka-connect sa mga speaker na microphone. So usahay collectively we call it the amplifier. But here in the study of basic electronics, when we say that the BJT is an amplifier, it's an active device that could increase or multiply the magnitude of a signal. Basic lang sa nga definition. Dili pa tong amplifier na system. So that's one of the application of the BJT. The other one is it could be used as a switch. So, lang, no? all the other applications of BJTs, pwede na to ma-categorize accordingly using these two applications. For example, we've mentioned earlier na ang mga microprocessors that are inside our devices like cell phones o sa laptops are made of transistors, right? Ang sasunod nga the inside the devices that are inside our microprocessors are transistors, no? So, haman to mabilong. If the transistor is used if the transistor that is used to build the microprocessor, no, kung ang transistor kay gamit para maka-create og microprocessor, actually that is just the transistor there is used as a switch, no? So on off la siya. That's why we have terms such as ones and zeros, right? Ones and zeros, on and off. Diba? Mag-switch will be gapon siya. So when the microprocessor uses transistors to process information, the transistors are used as a switch. Okay? So pa may other nga applications sa BJT. What if oscillator or filters, no? That are used in communication systems, modulators, no? So what are those? Asa man to siya mabilong, no? Those are under the category of amplifier, no? So most definitely, if most often than not, if transistors are used in telecommunication circuits, no, or electronic communication circuits, they are used as an amplifier. So for instrumentation, no, for instrumentation circuits in the industry, in industrial applications use transistors, no? So instrumentation, so asa man na siya under. Same gapon, no? Under na siya sa switch. So all of the applications or all of the functions, circuits, systems that we could that we know of, no, with regard to the use of the transistor, pwede na gid siya ma-categorize as either amplifier or switch, no? Kana lang yun. So if we know how the transistor works as an amplifier and how the transistor works as a switch, maski unsa pa nang klase nga circuit, we'll be able to understand it. So we've mentioned earlier the BJT voltages. Here are the BJT currents. So for the voltage, we have VCB, VCE, and VBE. For the BJT currents, we have IB, IC, and IE. So IB, IC, and IE corresponding to the three terminals of our BJT. So notice ilang mga directions. So for the NPN, so ignore na lang ning physical structure na illustration. Focus on taaning na ay schematic diagram. No? So tanaw na to first ang arrow sa atong schematic diagram. This one. No? So if asa ang arrow sa atong emitter na terminal, mo po ang direction sa atong emitter current or IE. No? Because sa arrow, paggawas siya, right? Meaning, diha mo gawas ang atong current IE. And siya lang paggawas. Ang IC is pasulod siya sa atong device. Si IB is pasulod po siya sa atong device. Okay? So how about sa PNP? This one, this is the PNP. How do we know? Because ang arrow is pasulod. Because the arrow is going inward, the emitter current will also go inward, IE. NC lang gihapon ang pasulod. IC now is pagawas, The same with IB. Okay? So, maras like reciprocal, no? Reciprocal ang operation sa PNP ug NPN. But in terms of analysis and design, wala kayo'y dako nga difference ang PNP ug NPN, no? In terms of analysis and design. Why? Because when we try to analyze and design electronic circuits, of course, we use mathematical equations. And I'm going to introduce now the first relationship that will define the currents inside or coming through the transistor. Okay. So, dili mag-matter if ang atong reference is NPN or PNP, this equation will hold, whether it is NPN or PNP. So, try to create a KCL equation based on these currents. No? So whether it is NPN or PNP, current IE will always be the sum of current IC and current IB. Diba? This is true for both PNP and NPN. For NPN, IE, pagawas, going outward, is the sum of IC and IB. So for PNP, IE, pasulod, is the sum of IC and IB, both pagawas. So sa mathematical standpoint, dili kayo dako og difference ang PNP ug NPN, pareha ra. No? Of course, in actual lagi na siya mga kalahian, no? Natay kinahanglan i-revise sa circuit if indeed we'd want to replace our transistor initially from NPN to PNP. Pero again, sa design, wala kayo difference. So this is the first of the few formulas that define our BJT. So try to memorize this one. No? Memorize na siya daan. IE is equal to IC plus IB. BJT characteristics defined by the characteristic curve. So this is the characteristic curve of our BJT. Okay. Characteristic curve. Mostly makita ning characteristic curve sa specification sheet of our BJT specs. Remember for the diode before, the characteristic curve of the diode looks like this. Diba? This is 0.7 volts. VD versus ID. Okay. Now, tungkol sa BJT, we have 3 pairs of currents and voltages. We do not need to look at each one of those. We'll only focus on the characteristic curve of the BJT with regard to voltage VCE versus current IC. Okay? Kailangan natin i-focus. Ano man, because most of the time, diyan nato i-connect atong load. So this is current IC. This is voltage VCE. Voltage VCE, current IC. This characteristic curve, actually we have 4 regions of operation. Tulo na nakabutang dire. Ma-mention early later sa slide ang other one, ako lang ibutang daan. It is the cutoff region. So these are the 4 regions of operation sa atong BJT. Okay? So ang saturation region is mag-make lang og estimate based sa given nato nga characteristic curve will be this one. This is a saturation region. Dealing area. Okay. Ang cutoff, pwede ganyan na ito i-approximate na below the x-axis. Pero pwede naman po dire. This is the cutoff region. Ang breakdown region, may can estimate lang gihapon. Masyag ingani, no? This region outside sa curve na line akong gidraw. So, any value diha, our diode is in the breakdown region. So, the most useful to us when we use the BJT as an amplifier, its region of operation should be the active region. No? Active region. This is when the BJT is used as an amplifier. So let's say, for example, no, in practice na, we have our tools, we have our multimeter. We'll measure voltage VCE. We'll use a multimeter to measure the voltage drop of VCE. So we obtain a value. Okay, maka-obtain tag value. Let's say the maximum VCE is, example lang, no? 20 volts. And of course, ang pinaka-ubos is 0 volts man gyud. Okay. Let's say ato nakuha nga value is somewhere in between. 10 volts. 10 volts ato nakuha nga value after measuring VCE. And using also our multimeter, we were able to measure the current passing through that piece of wire going inside the collector terminal. So na-measure na to na siya nga current using our ammeter or multimeter. Let's say, for example, ang maximum po dili nga IC is 20 milliamperes. Example lang. And the minimum is, of course, 0 amperes. Diba? So let's say somewhere in between, no? 15 or 12 or 16 milliamperes. Diha. So i-plot na to na points. I-plot na to ang 16 and ang 10. We have that point. Okay? So ang atong na-plot na point, we call that one the Q point. Or the quiescent point. Quiescent meaning stable. Muna siya ang point of operation, no? After putting our transistor maybe on the breadboard and then connecting to 8 resistors, no? Hook up na to siya og voltage source. Na siya operating point. No? So we could determine it using tools like oscilloscopes and meters. So we could also use this very useful, very useful na tool, the characteristic curve, to locate the Q point of our transistor. So if the Q point falls within the active region, so as an active region, na siya dire, no? Outside, inside this region, no? Outside sa active region, sa left na ang saturation, sa silong na ang cutoff, and ang nabilin is ang breakdown region. So for our transistor to be used as amplifier, we would want our Q point to be inside the active region. Okay? What if dako na kaayo ang current o voltage, no? Abot na og 22 milliamperes and abot na og 22 volts. No? So, ang Q point is nasa somewhere dire, na nasa sa breakdown region. So, ang mitabo sa atong transistor is mag-breakdown siya, maguba. So, we don't want that. What if bali? No? What if dako-dako pod ang current pero gamay kayong voltage, no? So a very large current somewhere here with a very small voltage, no? Almost close to zero. So ang atong transistor is used or is inside the saturation region. Ang opposite ato is very large voltage. Let's say for example 19 volts pero close to zero current, no? Almost no current passing through it. So na siya sa cut-off region. Easy to remember. Basta gani high voltage and no current. Right? When we say no current, it's as if na-turn off ang atong device. So na siya sa cut-off region. Saturated meaning, di ba? What do you mean when you say saturated? Napuno siya. As nato usually gina-use ng word na saturate ng sponge, no? With water. So ang sponge na to is napuno na og water. So if napuno na, na-saturate na siya og what with regard to the transistor, na puno na siya og current. So when we say it is saturated, high current and low voltage. Okay. So these are the regions of operation for our transistor. Ang breakdown region, nalang ni siya dire, just to let us know nga, kuan, no? No flying zone na siya diha. Again, if we want our transistor to be used as an amplifier, we should locate our Q point to be inside the active region. So what if ang atong Q point is nasa saturation or cutoff? No? Maguba bang diode? Ang transistor? No, di siya maguba. Of course, ito lang siya maguba kung nasa breakdown region. So, if our Q point is changing its region operation from saturation to cutoff and cutoff to saturation, vice versa, di ba? It's as if it acts as a switch. So diyan na din mo gikan katong atong two main functions of our transistor. Our transistor could act as an amplifier or as a switch. So how will we properly bias our transistor para amplifier lang siya or switch gyud siya? Ato i-locate ang Q point sa characteristic curve. So kung amplifier, nasa active region. Kung switch, mag-switch siya from saturation to cutoff and vice versa. So how will we bias our transistor para magamit siya as amplifier or para magamit siya as a switch? Ano naman tayo idea before sa amplifier? Diba? In normal operation, the base emitter is forward bias and the base collector is reverse bias. So, ano to? Ang base emitter region is naka-forward bias while ang collector base region is naka-reverse bias. If we bias it properly, now we connect the right amount of resistors and the correct amount of voltage source to our BJT, pwede na ito mabias properly in the active region ng atong transistor. So about for the switch, or the transistor as a switch. In the saturation region, no, for a transistor to be in the saturation region, we need the base emitter and the collector base regions both to be forward biased. Whereas a cutoff, both base emitter and collector base naka reverse bias. So yan na lang ka simple. No? So far, before I proceed, any questions? Siguro complicated lang ni paminawan karon. But if maabot ta sa analysis and design of circuits, you would appreciate nga mas sayon siya, no? Mas simple kaya siya kaysa sa diodes previously. Mas heavy lang ni siya og kuan, no? Concepts and theory. So if makuha na to ang concepts of theory sa BJT, mas sayon na ang iyang computation. Okay. So let's not forget that whether as amplifier or switch, the character of our BJT from IC to IE, okay, flowing from IC, from the collector to the emitter through IC and IE. So large amount of current na siya. Where will it depend? It will depend on the very small current IB. Gamay lang ako to emphasize nga gamay ang IB compared to IC ug IE. Si IC ug IE are both in milliamperes range, no? Milliamperes range na sila. Whereas IB is normally naka-microamperes ang IB. IC and IE are most definitely 100 times larger than IB. So ang main yun na capability, no? Of course, ang main na function or application sa BJT is again, it could either be used as an amplifier or switch. But yung main capability is for this small current IB to control the very large current IC and IE. No? So, kung amplifier siya, if IB is small in magnitude, i-control niya ang a very much larger current na IC and IE. Kung saan characteristic sa IB, sunon na siya ni IC and IE. So in that sense, diyan na dahil mo siyang pagka-amplifier, di ba? Because gi-follow ni IC and IE ang itsura ni IB, malag as if iyang gi-amplify ang iyang self, no, iyang kaugalingon. Depende sa itsura ni IB. So mo gina iyang main nga capability. So because there is a relationship, or I mean because IC is controlled by IB, in this case, there exists a relationship between IC and IB. So there exists an amplification factor, or what we call a DC current gain. A DC current gain. Or, shorthand ana, we use this term, beta. Beta is the ratio of the collector current to the base current. So, beta is equal to IC over IB. So, kung sa itsura ni IB, o pala itsura ni IC. Pero mas dako lang. No? And how much larger? What is the amount? The amount is beta. So this is the second relationship that defines our transistor. So ako lang nang i-rearrange so that it will be IC is equal to beta IB. Most of the time, beta is given. So if beta is given, and na-obtain na to si IB, i-multiply lang natin siya beta to obtain IC. So try to memorize na this one. Itong first, IE is equal to IC plus IB. The second is IC is equal to beta IB. So how will we measure beta based on the characteristic curve? Okay. Remember previously, na ang atong x-axis is VCE, and atong y-axis is IC. So IC ni siya nga axis nasa vertical line. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliamperes. Okay. Kaning mga lines dire, kani class, these are the different possible IBs, no? Mga IB. Notice IB0, IB1, IB2, IB6. So this might probably be 0 microamperes, no? Maybe 1 microampere ni siya, kani is 2, kani 3, kani 4, kani 5, kani 6 microampere. So asaan na itong pilion? Depende sa atua, no? Depende kung sa itong na-measure or depende kung sa itong gusto. So we've learned previously nga ang active region is somewhere down the middle, no? So let's say we want to utilize 4 microamperes as our IB. Okay? So 4 microamperes. So we'll use this characteristic curve. Then ignore na lang yung tanan. So if nakapili na tao IB, if nakasolve tag IB, ignore na lang uban. Hindi na magamit. So we'll use 4 microamperes. So asa siya mag-fall, no? Then depende sa atong VCE. Let's say this is our VCE, 10 volts. And we'll use 4 microamperes. So ato nang i-project dito kung asa na siya mo fall sa IC na axis. So siguro, no, kung estimate lang, siguro sa mga 6.5 milliamperes. So muna siya ang atong IC. So how will we get beta? Just divide IB and IC. So in this case, beta is equal to 6.5 milli divided by 4 micro. Notice nga laylay sila og kuan, laylay sila og unit of measure, no? Milli og micro. So kasi na calculator pwede makasolve ana. .5 milliamperes divided by 4 microamperes. Okay. 1625. Should ako kain eh. Pero sige lang, no? For the sake of, kung ano na siya. For the sake of example. Wala na may beta nga mabutog yan nakita ko. So, dili na siya realistic na value actually. No? So, Paano niya siya? No? Para lang atong ma-illustrate sa pag-compute sa beta. In practice or in actual, si beta is nasa mga 50 to 400. Narana, no? Nakuha kayo ng 1625 wala beta yung ana. Okay. So again, IC is equal to beta IB. Ano, example gid mas better ning example. So 5 milliamperes ni dire. And yung gi-choose na beta is, or IB is 30 microamperes. So 5 divided by 30 na siya. Okay. So this is the cut-off region. I have explained this kanina na. And the saturation region. So same gapon. No? So for cut-off, ito lang i-remember, no? When the amplifier, when the transistor is used as a switch, it utilizes both the cutoff and the saturation region. So mag-switch siya from cutoff to saturation, from saturation to cutoff, vice versa. So for cutoff, ito lang i-remember, no? So ito na point out kanina, that both the base emitter and the collector base are reverse bias. Or in more practical terms, VCE is maximum, no? Approximately equal to kung ano ganit, no? Pwede natin approximately equal to the voltage source. And IC is 0. So manapos sa cut-off. Much like an open switch. Diba? Much like an open switch. If ang switch is naka-open, meaning it is off. And when it's off, no current will pass through it. So current is 0. And if magbutang taog multimeter measuring the voltage across the switch, the open switch, ang atong ma-measure is ang source. Right? So voltage is maximum when the switch is off. So remember na basa, ECE is maximum, IC is 0. Because it is switching from cutoff to saturation, inverse ani ang may tabo during that region. This time, VCE is almost equal to 0. And IC is maximum. Saturated IC. Same gyapon sa isa ka closed na switch. Kung mabutan taog voltage, voltmeter dire sa closed switch, makuha itong measurements atong voltmeter is 0. And the current na mag-flow through it is the maximum amount of current na i-supply sa atong source. Much like a closed switch, no? Or a switch that is turned on. So try to remember lang these ones. DC load line. Siya, no? This is the tool that we'll be using we will use to determine the Q point. So the example dili. For a more accurate treatment sa atong computations analysis, mas better ta magamit sa mga formulas na atong na point out na kanina kaysa sa DC load line, no? if wala tay accurate kayo nga characteristic curve, so kay gamit ang DC load line, no? So we'll refrain from using this one. We can only use this one to visualize, no, the concepts. Pero in practice, mas better gito mga formulas. So sa data sheet, I think ang gina-point out direct, dito makita sa data sheet ang beta. But basig wala tayo ma-notice na to, wala tayong makita nga Greek letter beta sa characteristic, sa specification sheet. No? Ang beta is equivalent to HFE sa specs. No? Wala pa gyapon gipulihan sa mga manufacturers. Karaan na siya nga term ng HFE, utilizing the H model for transistors, I think. So, tungod kay daghanag na anad, no, sa H model. So, HFE pagyapon ang beta sa specs. Diba? Muna akong gi-mention earlier. Bjts Amplifier. A very small signal sa base will be amplified at the collector. Switch off. No? Explain kanina po. Phototransistors. No? Phototransistors are a specific example, no? Specific kind of example for BJTs. Instead of an actual current source na itong i-connect sa base to produce the signal, here, light will produce the base current. So when the base will be struck with light, current will flow in the base na terminal, and it will control the much larger collector current. So asa ni may use ang phototransistors, or kung ato siyang i-tandem with LED as the light source, no? So this is the phototransistor. And this is the LED. Ang LED ang mag-supply of light source atong phototransistor. So as in usually nato makita, this could be used, or we could build a very simple security system out of this setup. No? Na may mga available na optocouplers naka-package na. But we could create our own optocoupler. No? Kahit lang tawag separate ng LED phototransistor. Example, nato ni kabit. Pwede nato ni ibutang sila sa atong door, no? Kaning isa, perhaps, ang LED is nasa door frame. Ang phototransistor mismo is nasa door. Kanabi taong sa door na to, no? Mamuning door frame. Frame na nakalagay sa wall. Mamuning ang door. Buta na to ang atong LED dire o ang phototransistor here, such that kung naka-close ang door, no? Meaning kung naka-close ang door, meaning ma-receive sa phototransistor ang light na gina-produce sa LED. And once mag-open ang door, no? Kung mag-open ang door, meaning physically separated na si LED o si phototransistor, dili na ma-receive ni phototransistor ang light ni LED. So iyan ang ma-detect. Pwede na to ni kabitan o alarm system, no? Or bell alarm. In such a way na kung indeed ma-physically separate si LED from the phototransistor, current will flow, di ba? The light will be converted to current IB. And IB will control the much larger current IC. So if IC is produced, because IB is produced from the light source, the alarm will turn on and mag-sound the line siya. So intruder alert, na-open ang door, So very simple, no? Although modern security systems are more sophisticated than this one. So kung gusto mo magbuhat sa inyong own nga room lang, no? Sa inyong balay, kung mo gusto nga musulod yung manghod, kung makabalo mo kung gusto yung manghod or wala, and so on, no? Pwede lang mabuhat yung ani, no? Optocoupler using LED and phototransistor. So although simple lang ni siya ng example, this is still the basis. No? Mao gyapon ni siya ang basis for more complex and complicated security systems using instrumentation circuits. Mahulog man nga kani is a very crude nga instrumentation circuit. So optocoupler. So man ni siya amplifier or switch? Switch gyapon. So the transistor here in the form of the phototransistor is used as a switch. This amplifier. Another application for optocoupler is a traffic controller. Pwede natin ibasahon. So these are the different available packages manufactured for the transistor. Something as basic as this one. I think mo na usually ito makita kung mag-open ta og kanang appliances, no? Appliances, TV. Kung mga karaan nga TV, makita tao three-legged na device, most probably transistor to siya. Apoy usahin nga ani, no? Common po din siya nga transistor package. So sa sulod ani is na dito ang atong transistor, no? Maybe ang ana, no? Base, collector, emitter. So nasa sulod ang transistor, no? Ka-wrap na siya o plastic, what we call the epoxy. Epoxy ang type of material aning coating. This one is a metallic heat sink. Because the BJT is still an electronic device, it will heat up kung init din na siya. And kinanglan o proper sinking of the heat para ipalayo, no? Ipahawa ang kainit sa or para dili ma-contain, no? Para dili ma-contain ang kainit sa atong transistor within itself. Because we know previously, even sa mga diodes, nga directly proportional current nga gapass to sa electronic device sa semiconductor material and sa ambient temperature. So kung mas init siya, mas init ang environment, mas init ang device mismo, kato atong mga calculate ng mga values, dili na to sila mga actual kay mas init naman. Assumption man sa mga calculations natin is room temperature. So dininin mo sulod si heat sink. I-divert niya pagawas ang heat na na-generate sa transistor. So how do we test if our BJT is working? No, we'll just use a multimeter, such as this one. So ibutang lang nato ang atong positive terminal sa multimeter sa emitter. Sorry, sa base dapat sa base. So the positive terminal should be connected to the base, while the negative terminal connect nato sa atong emitter. So how do we know if our transistor is not yet busted? If we'll obtain a voltage drop. And this is now the third characteristic of our BJT. We know it is working if ang voltage drop across the base emitter junction is 0.05 volts. And that's constant. So because our transistor is made of silicon, na siya voltage drop diyan na 0.7. Malagyan po diode. Exactly like the diode. So balik na itong mga BJT voltages. We have the VBE, VCE, and VCB. VBE is constant. No need to solve. Always equal to 0.7 volts. VCE can be calculated or given kung design. VCB, for analysis and design purposes, ignored. So remember, when we use the BJT as an amplifier, the collector-based terminals or the collector-based region is reverse bias. So in analysis and design, ato lang na siyang gina-ignore ang VCB. Ang VCE, given 0.7. Ang VCE lang kibalig yun ang gina-solve. So isa lang ka voltage ang gina-solve, VCE lang. Okay? Okay, so that ends our introduction to the BJT. Ako yung notes gahapon, nag-isulat sa pikas klase. Madala. So ako na din i-summarize ang formulas na gamiton for the BJT. So these are the first three that I have introduced earlier are these. Muna na siya ang mga important na formula nga itong i-memorize. Formulas 1, 2, and 3. Si Formula 4, this one, is derived when we substitute Formula 2 to Formula 1. Notice, IE is equal to IC plus IB. But because IC is beta IB, pwede lang na i-substitute dire. No? So IE then is equal to beta IB plus IB. So IE is beta IB plus IB. So pwede na ito i-factor out si IB. Therefore, IE is equal to beta plus 1 IB. That is formula number 4. IE is beta plus 1 IB. Derived na siya from 2 and 1. Formula number 5, which we will only use when atong application is switching. For amplifier, we'll not use formula number 5. So in switching applications, we could approximate IC to be equal to IE. Why? Because IE and IC are all in milliamperes and IB is in microamperes. 100 times larger si IC compared to IB. So pwede na nato negate, or make negligible si IB. For example, IC is 1 milliamp, and IB is 10 microamperes. Kung i-add na to silang duha to get IE, we have 1.010 milliamperes. So pwede na negligible na si IB. Okay? So ang very useful lang yun here is formulas 1, 2, 3. Okay, today, BCE is calculated, BCB is ignored. Right. Is it clear? Questions?